Good afternoon to you there. Sorry for the little delay. Had some scheduling issues here. So this is a school. So what I thought I would do today is give you a tutorial type presentation about the neutral atom approach to quantum computing. And then towards the end, I'll share some recent progress both on gate operations, but also on running quantum circuits. And although it can be difficult to connect with the audience while presenting in this way, I do encourage people to interrupt with questions as I go along. I'm happy to make it a interactive presentation. Okay. So, this is part of the worldwide effort to develop quantum computing systems. And I think, as everyone knows, there is a handful of approaches that are being very actively developed these days to enable quantum computation. And roughly speaking, you can divide the most active approaches into a couple of types. So there's the atomic qubits, trapped ions, and neutral atoms. And these generally work in a room temperature apparatus. There are some benefits to cooling to, say, 4 Kelvin, but we don't need the very deep millikelvin cooling that's required for the superconductor and quantum dot approaches. The atomic approaches have the very advantageous feature that all the qubits are identical. These are natural qubits. They're essentially free. They're all the same. And this is a very strong feature for implementing quantum computation. We use optics and lasers to control these atomic qubits. And therefore, it's quite natural to include them in quantum networks using atom-photon interfaces. And perhaps on the downside, because we use lots of lasers, we're also dependent on the laser technology, which, to be honest, is not as well developed as electronic technology. You can contrast the atomic approaches with the solid state approaches, be it superconducting circuits or quantum dots. These are engineered qubits. They're not identical, so that adds some overhead to system operation. They do require cryogenic cooling, deep cryogenic cooling to millikelvin temperatures in dilution fridges. There's no direct optical interface. Lots of people are working to tackle this problem. And then, nicely, they rely on microwave electronics, which is a very well-established and available technology. And then I'll mention a little bit over to the side, there's also the optical approaches, be they single photons or squeezed coherent states of photons. Different people have different opinions about the optical approach. I'll just say the scalability is challenging. Memory is difficult, and because there is no deterministic 2-qubit gate, at least not available today, that does make scalability challenging. This is perhaps a little inappropriate, but I'll just mention if you're interested in taking a deeper dive into these technologies and getting a physics overview of them, I'll mention a recent book that I wrote with Janos Bergo and Mark Hillary, and the last third of this book has chapters that cover all of these platforms in detail, where you can read in much more detail about these different approaches. Okay, but today I want to talk about the neutral atom approach, and but maybe before doing that, I'll just one more general slide here. As we know, quantum computing is difficult, and it's really difficult because we're trying to merge conflicting requirements into one system. Quantum computation relies on full control of the qubits and strong coupling between qubits to implement logic. At the same time, maintaining the quantum properties of superposition, entanglement, requires a very weak coupling to the environment. You have to isolate the qubits from the environment. On the other hand, we need that coupling to control the qubits, to measure the results, and eventually for error correction. And so maintaining both strong coupling and weak coupling in one system is contradictory, and So these different platforms provide different approaches to solving this challenge. Why do we think neutral atoms are an interesting approach? Well, it's an interesting platform where we indeed can satisfy these conflicting requirements of isolation and control in one system. So we have laser-cooled atoms trapped by light and vacuum. They're extremely well isolated. And although I wouldn't say we've achieved minutes yet, in principle, we think we can maintain quantum coherence in this system for minutes, and certainly several seconds have already been achieved. So we have excellent quantum memory. We have selective control by focusing laser pulses onto individual atoms. And by exciting to these Rydberg states, we can turn on very strong interactions. And remarkably, the ratio of the Rydberg interaction to the ground-ground interaction in the memory state is about 12 orders of magnitude. So this very large on-off ratio is enabling for implementing quantum logic. Another aspect is the large potential connectivity. By going to these high Rydberg states, we have very strong interactions, which means we're not limited to nearest neighbor interactions, but depending on which Rydberg state we access, we can envision going up to having very long-range connectivity many sites away in a dense array of qubits. And one might compare that, for example, with some of the latest architectures in the superconducting world, where the connectivity is just mostly nearest neighbor, with some sites having 3-qubit connectivity, but many sites just having 2-qubit connectivity. So there's an advantage in connectivity with this atomic array, and that really translates into algorithmic performance. So supposing I'm implementing a quantum circuit where I want to entangle a qubit A on the left with the qubit B on the right. If I'm limited to nearest neighbor interactions, I need to move the quantum state over using swap gates. And even if the intrinsic 2-qubit fidelity were 2 nines, it takes 3 C0 operations per swap. I would need 28 gates to connect A to B, and that 0.99 to the 28th would be a much smaller number. I might contrast that with a future atomic system where I have much longer range connectivity. Supposing I had long enough range to get halfway across. So to connect A to B, I'd need 1 swap and 1 C0. That's 4 gates. And even if I started with a lower fidelity, I'd end up with a higher fidelity for that operation. So certainly the connectivity is very important for laying out circuits and actually performing computations. So with that brief general introduction, maybe a very brief history of this neutral atom approach. The original ideas go back about 20 years to the early 2000s, late 1990s, where various protocols were proposed for using neutral atoms for quantum computing. The first demonstrations of quantum state control of single trapped neutral atoms from the early 2000s by a number of groups approaching the problem in different ways. About a decade later, we saw the first demonstration of universal gate set for neutral atom qubits and preparation of Bell states. That was done by our group in Wisconsin, and also Philippe Branchet, Antoine Brouet's working in Paris. A few years after that, we started to see arrays of tens of controllable atomic qubits. I mean, I should say in the cold atom community, people have been working with lattices of single atoms much earlier than this, but sub-wavelength spaced atoms. And so it was really not till this time that we saw these more widely spaced atomic arrays that were compatible with individual optical addressing. A very important development in the field that came a couple years later was the development of rearrangement techniques or atom by atom assembly to completely fill patterns of atoms to make it suitable for quantum computation. And that work was developed both in Korea at Harvard and in Paris at about the same time. And a few years after that, we started to see very high fidelity 2-qubit gates. And the current record is a Bell state of 2 strontium atoms done by the Enders group at Caltech with fidelity greater than 2 nines. And The current challenge, in my opinion, is to combine this high fidelity operations with multi-qubit arrays and build a computer. And that's what we and many others are actively engaged in. There's really two modalities of operation with neutral atoms, and you can divide them into analog and digital. There's the analog simulators, and this approach is exemplified by really beautiful recent work from the Lucan group at Harvard and the Broes group near Paris, where they've used arrays of several hundred atoms in an analog simulator modality, essentially implementing transverse Ising models with the Rydberg interaction to generate various many-body quantum states. This analog approach has relatively simplified control. It's partially programmable, but not universal. And there's not an obvious path towards implementing error correction for making very long calculations. So the analog approach can be contrasted with digital gate model circuits. This is what we're trying to do in Wisconsin, and really this is a collaborative effort with the Cold Quanta company, which is seeking to commercialize this approach. And there we have our array of qubits, but we're performing traditional quantum gate circuits. So here's an example of a QAOA circuit and an output state distribution. This digital gate model approach really gives us requires full quantum state control. It's universally programmable, so not just Ising models, but a very large range of problems can be solved. And although challenging, there's a very clear path towards error correction and fault tolerance. And so what I'll talk about today is the digital gate model approach. Here's a picture of my lab in Wisconsin. Usual mess of lasers and electronics and optics. The actual quantum processing unit, or QPU, is sitting back here. When we're actually operating, there's a box around it to give a temperature stabilized environment. And a little bit closer look inside there. It's hard to see what's going on, but the vacuum cell is at the center of this, and there's a large collection of optics for laser cooling, for defining trap arrays, and for steering control beams using acousto-optic deflectors to target individual atoms. So, any approach to quantum computing needs to satisfy a set of requirements, and these were formalized by David DiVincenzo many years ago, and it's a fairly obvious set of requirements to implement quantum computation. We need to initialize qubits, they need to have good coherence, we need to be able to measure the results, we need a universal set of logical gates, and it has to be scalable. And I'll walk through how we approach satisfying these different requirements using neutral atoms. Just a comment on this slide, scalability, one can analyze the system and predict that it's going to be scalable, but there's never any proof of scalability before actually building it and demonstrating it, because there may be all the things we didn't think of may in the end make scalability challenging. So it's really, you cannot provide an upfront proof, you have to do it to show that the system is scalable. So which atom should we pick? There's a lot of atoms out there. Some of them are easier, some are more difficult to work with. Certainly in terms of neutral atom quantum computing, the attention is focused on the heavy alkalis, rubidium and cesium, and our work is primarily using cesium. There's also been a lot of recent efforts on strontium and ytterbium, and indeed the highest 2-qubit fidelity today, or 2-atom entanglement fidelity, is with strontium. There's aspects of the alkaline Earth-like atoms which make them very interesting for quantum computing, in particular the presence of metastable states and the connection with atomic clocks. Nonetheless, I'd say the jury is out as to which of these types of atoms are going to be most appropriate for quantum computation. But I'll talk today about cesium. And the cesium atom gives us what I like to call tongue-in-cheek as an industry standard qubit. We're using the hyperfine clock states. These are the same states that provide the SI definition of the second. The second is defined in terms of the frequency of resonant radiation connecting those two states. These two basis states are themselves entangled superpositions of nuclear and electronic spin projections. It's entanglement that occurs in nature, but it's not a kind of entanglement that's directly useful for quantum computation. Qubits encoded in these states have excellent coherence properties. In free space, the hyperfine lifetime is many years. And when optically trapped, coherence times T1 and T2, up to about 10 seconds, has been demonstrated. The achievable coherence is really limited by the finite atom temperature, trap light induced optical stark shifts and magnetic fields. And I want to take a few minutes now and go into a bit more detail on the atomic physics that concerns the coherence of trapped atomic qubits and point out what the current limitations are and what the one possible path is towards achieving much longer coherence than has been demonstrated to date. So that understanding the coherence of those qubits is the first step in the operational sequence. Before getting into those details, let me just list the sort of steps needed. We need to first cool atoms with laser cooling. We need to then load them into some trap array so we have well-defined qubits. And then we need to do some rearrangement to fill up the trap array to provide a quantum register. And I think of that as controlling the mechanics, the actual mechanical motion of the atoms. And then the next step is the calculation cycle, controlling the quantum states, which involves state initialization, running a quantum circuit, and measuring the results. In terms of the optical trapping, there's really two basic approaches using light fields. There's red detuned traps, where the light is at a lower frequency than the strong transitions out of the ground state. This provides an attractive potential for the atoms, which are combined at positions of maximum intensity. So this is most directly implemented just by focusing a laser beam down to a small spot, the so-called optical tweezer. And so there we have a local maximum of the intensity, which gives us a local minimum of the light shift potential. And this is very good for atom transport and filling the qubit register. The other approach is a blue detuned trap, where the light is at a higher frequency. It provides a repulsive potential to the atoms, and the atoms are therefore confined at the local minimum, or even a zero, of the optical intensity. So this has the nice feature that the atoms are sitting in a region with much lower light intensity that gives reduced decoherence, reduced scattering rates, reduced stark shifts. The cost of that is that the optical system for producing these local minima tends to be more complicated than in the case of the tweezers. And this approach can be used for holding qubits with very long coherence times. In my group, we've worked on a number of different ways of generating these blue traps over the last decade or more. You can prepare single bottle beams, local minima of the intensity surrounded by light in all directions. There's different ways of producing these beams. We've produced arrays of them using diffractive elements. We've then moved to something in this paper we call the Gaussian beam array, where we use weakly overlapping Gaussian beams to provide dark spots in between the beams, where we also can trap atoms. More recently, we're using something we like to call a line array and a dynamic line array, where we set up a grid of lines of blue detuned light. The atoms are trapped in these cages in between each unit cell of the grid. And if you were to propagate the light out of the plane, these cages fill in due to diffractive spreading of the lines. We're also right now working on a new, more scalable, simplified approach that we call a whole array, which uses a fabricated component to generate more than 1,000 sites where we have these localized dark traps. So this line array can be dynamically controlled. It uses acousto-optic deflectors to select the number of lines and their frequencies. And this approach scales up to about 500 sites. Beyond that, the lines get very long and very thin, which makes the optics difficult. This new whole array approach we've been testing out, and here's a preliminary picture of about 700 cesium atoms trapped in a very simple trap array approach. So going back to the qubits themselves, as I mentioned, we're using the m=0 clock states of the cesium atom, which has this frequency, about 9.2 gigahertz. And let's look in some more detail about what sets the limit on the coherence of this encoding. And it's important to have as long coherence as possible in order to reduce errors and, in looking to the future, reducing the burden of error correction for scalable quantum computing. So there's a sort of fundamental limit, and that the energy of the f=4 state is slightly higher. In a room temperature bath, the lifetimes of these states are about 35 years, so we're going to ignore that limit. But then there's other more important limits. One is magnetic noise. So although these are m=0 states, they have a quadratic sensitivity to magnetic fields, and you can write out what that is in terms of hertz per Tesla squared. That sets some limits, and more importantly, there's an intensity-dependent clock shift. So when we put atoms in these optical traps, these two states, f=3 and f=4, although this is an angular momentum of 1/2 state, there's a small tensor polarizability, which gives a differential shift, and that leads to decoherence of the atomic qubit. Decoherence because, on the one hand, the intensity of the trapping laser is never perfectly constant. There'll be some fluctuating noise on the intensity, which leads to fluctuations of that energy difference. And if the atom is not cooled to the motional ground state, it will be moving around a little bit in this trap, sampling regions of different intensity, and thereby also causing intensity-dependent clock shifts. So, one can look at that, and the scenario is the following. We have a qubit encoded in these hyperfine ground states, and there's the light that's providing the trapping potential is at frequencies of hundreds of terahertz, coupling up to excited electronic states. If we zoom in on the qubit frequency is order some gigahertz, 9 gigahertz in cesium, other amounts in other atoms. And then if we zoom in on the motional states within the potential, they are slightly displaced for the 0 and 1 qubit states because of the tensor shift, and that differential light shift tends to be in the kilohertz range. Depending on the strength of the confining optical potential, the harmonic oscillator spacing of the motional states is a few kilohertz up to possibly megahertz, although that's sort of somewhat extreme for neutral atom traps, but it could approach megahertz. But the differential light shifts are typically order kilohertz. And there's an old calculation that goes back to the Dieter Mescheday's group in Bonn from about 15 years ago, where they analyzed this problem semi-classically and expressed the T2 star due to this differential light shift in terms of the differential light shift itself, that being the fractional difference of the light shift seen by the two qubit states. So this expression here, so the T2 star is inversely proportional to that differential light shift. Smaller shift gives longer T2 star, and it's also inversely proportional to the temperature. This is a semi-classical result, and the temperature determines how much excitation there is in terms of the vibrational levels. So this is an old problem. It's been analyzed by many groups, and also recently by the neutral atom group in Moscow has a nice preprint out on this problem. So, those light shifts, you can analyze it semi-classically, as was originally done. You can also do a full quantum calculation, including quantization of the motional states of the atoms in these traps. And here's a sort of sample results for particular parameters. Here I've taken trap vibrational frequencies of 50 kilohertz radially, 10 kilohertz axially, a fractional differential light shift of a few 10 to the minus 4. This corresponds to cesium atoms in a 780 nanometer trap. This is one of the wavelengths that we use for this. And as a function of the atomic temperature, I'm plotting the T2 star from a semi-classical and a quantum calculation. The full quantum calculation actually shows you have longer coherence time as you get very cold, which corresponds to starting to get substantial occupation of the vibrational ground state. And you can see that this T2 star goes up into the 0.1 seconds or 100 milliseconds and more at low temperature. So this problem has attracted a lot of interest over the years, not just for quantum computing, but really also in the context of atomic clocks. And people have looked at this and also looked at ways of engineering the traps and engineering the structure, including the polarization structure of the light fields, to minimize or cancel these differential shifts to give so-called magic trapping conditions. And something that became apparent a few years ago from our work and that of others is that, somewhat surprisingly, it's not sufficient to consider just the intensity-dependent light shifts, but one has to also include the hyperpolarizability. So that is, one has to calculate these light shifts at fourth order in the optical field. And doing that, one finds that the notion of magic wavelength, which is prevalent in optical atomic clocks, is really not what descriptive of the situation here. It's really a situation of a magic intensity value. And we calculated this some years ago, and it was also verified by the group in Wuhan experimentally. And so here's a plot that shows this. If one ignores the hyperpolarizability and calculates the differential shift of these cesium clock states versus the trap depth. And for a blue trap, the trap depth is just the light shift at the bottom of the trap. One has a linear dependence, just including the second order effect, but including the hyperpolarizability, there's actually a particular value of the trap depth where the derivative of the light shift with respect to the trap depth is 0, so that's the magic intensity condition. So it's important to go to higher order in that analysis. And ideally, we'd like doubly magic traps where we can cancel both the dependence of the light shift on the magnetic field and on the intensity simultaneously to get the longest possible coherence time. And in fact, the magnetic shifts and the optical shifts are coupled. So there's coupling between the Zeeman shift and the light shift. And so here's the plot I just showed you, showing you the importance of the hyperpolarizability in the optically induced shift. And here you see the differential light shift versus the magnetic field without including a cross term coupling the Zeeman and light shifts, and including that cross term. And you see that the position of the magic point, the zero derivative point, is actually substantially shifted, including the cross term. So it's necessary to make a more detailed analysis. And I'm going to just sketch out how that proceeds now. So there's two contributions to this differential shift. There's the Zeeman shift proportional to the magnetic field, and there's the light shift, differential light shift proportional to the Rabi frequency of the trapping light, or that squared being the intensity. And there's a number of terms to consider. There's the linear Zeeman shift, which may be 0 for the clock states, but non-zero for other states. There's the quadratic Zeeman shift, which we see for most states. There's a tensor, effective tensor polarizability of the ground states proportional to the intensity of the light. There's a hyperpolarizability proportional to the intensity squared. And there's also a cross term. And the leading cross term is a occurs at third order. It couples the field squared or intensity times the magnetic field. And so one has to include all those terms in calculating the light shifts. And doing that, it turns out that with monochromatic trapping light, there really are not any double magic conditions. This is a different result than was found earlier by others. What we did find, though, was that by dressing the trapping light with sidebands, one can find doubly magic solutions where we have a magic condition for both the magnetic shifts and the light shifts at arbitrary trap depths and wavelengths by varying the frequencies and strengths of additional sideband fields that couple different vibrational states in the trap. And at this point, the calculation gets technical, but just to highlight some of the results, assuming, for example, magnetic noise of nanotesla, one can, at a magic point, calculating the second derivatives of the residual shifts, one can expect magnetic lifetimes that could be, or decoherence times that could be extremely long, measured in hours. Light shifts that are also very small, corresponding to coherence times of minutes. In reality, coherence limits will be set by photon scattering, but it looks entirely plausible that we could reach minutes of coherence time in this system. So that was a lot of detail about that aspect, but I think it's a very important aspect as this approach to qubits progresses to really do the optical and system engineering to achieve these long coherence times. Another aspect of these blue traps is that they can be used to trap both ground state atoms and Rydberg states. The Rydberg states you can think of as free electrons. The valence electron that's excited to a Rydberg orbital is very far from the nucleus, and it's not in a free state. It's still bound, but it's far from the nucleus, and it has a negative polarizability just given by the Ponderomotive effect acting on that Rydberg electron. And so when we go to these fluty-tuned traps, we can trap both the ground state and the Rydberg states simultaneously. And here's an example, some old data we took showing that with the traps on, we have a much longer trapping lifetime compared to the traps off. We're looking at the 61D cesium Rydberg state, and the trap on lifetime is also limited by just the natural spontaneous radiative lifetime. If one accounts for that, one can back out a mechanical lifetime of the Rydberg atom in these traps of more than 300 microseconds, which is much longer than the gate times we use. And this has been demonstrated in further detail by several groups in the last few years. Okay, so that's about the trapping. Another important aspect is that of atom rearrangement. When we load atoms from a magneto-optical trap into these arrays of optical traps, ideally we want to have a single trapped atom in each trapping site, but generally we get some picture like this where we have a stochastic distribution of atoms in the trap array. And then one uses rearrangement techniques to deterministically move the atoms around. One takes a picture of where the atoms are and then moves them to desired locations. And probably the most beautiful demonstration of this is from Antoine Brouet's group, where they built an Eiffel Tower out of individual atoms a couple of years ago. This is now being demonstrated many places and has become a standard technique in the field, including this recent work in Moscow. In Madison, we've also been implementing this in 2D arrays, and I would not say we've done anything special, but it's working in a very reliable way. And here we wrote out physics using our trapped cesium atoms. Moving on to the problem of qubit measurement. So we have our qubits encoded in these hyperfine states, and at the end of a calculation, we need to determine what the quantum state is to extract the results of the measurement. And we generally do that by light scattering. And so in principle, I can cycle an atom from the f equals 4 state up to the f equals 5 state of the 6b3/2 level. at 850 nanometers, same transition used for initial laser cooling. Because of selection rules, the F equals 5 state can only decay back to F equals 4. So I scatter photons, record them with a camera, and generate histograms that give very well resolved measurement of these states. So that's the ideal situation. Reality is a little bit more complicated because although 4 to 5 is a cycling transition, there will also be off-resonant excitation of these other excited states, which leads to Raman transitions. So the simplest way of performing a state measurement despite the presence of the Raman transitions, and here you see, for the example of actually rubidium with F equals 1 and 2 ground states, I may try and excite from 2 to 3 prime, but there will be some off-resonant excitation of these other levels that can decay down to F equals 1, which corrupts the quantum state. So the way we deal with this is to blow away or push out atoms in one of the hyperfine levels and then check for the presence of an atom. The downside of this approach is that we need to reload an atom after each measurement, which gives a slow data rate. We have to redo the cooling cycle, prepare the mod, load the array, and so on. So this is not desirable. We can make a QND state measurement. And the way to do that is to use sigma plus polarized light. And what that will do is pump the atom over to this state, 2, 2 state, and then the sigma plus polarization will only drive from 2, 2 to 3, 3, and then we don't have any Raman transitions because the state can only decay back to F equals 2, and using sigma plus starting from this state, there's no coupling to these other F prime equals 2 states. So that was initially demonstrated for single trapped qubits using photon counting detectors about 10 years ago. And more recently, this has also been demonstrated with small arrays of atoms. So here you have a diagram of the setup. There's a array of here 5 atomic sites, and we use counterpropagating sigma plus light to pump the atoms over to 2, 2, and then cycle without Raman transitions. And we were able to get not perfect, but quite good state measurements with fidelity of about 97% in about 5 milliseconds. So that was described in this paper, similar result from the Meshadi group in Bonn. And we have so far only demonstrated this on a relatively small array, but I think quite soon we'll be able to show this working well also in one of these larger 2-dimensional arrays. Okay, so those are the steps for controlling the mechanics. And maybe at this point, I just stop for a second and ask if there's any questions about the material I've covered so far.
No, I think we'll arrange the questions at the end of the lecture.
Okay, very good. So let me continue then with controlling the quantum state. So the starting point of that is optical pumping into one of the clock states. We do this using fairly standard techniques, and we get pumping fidelities of better than 2 nines in 100 microseconds or so. So let me not dwell on that. That works well, and move on to the qubit control. So we have a lot of different lasers and wavelengths that we use for this. We have our qubit in the ground states. We have microwaves for controlling the ground states. We're using the first excited states for cooling, for optical pumping, for readout. We use the next excited state for single qubit gates, and then 2 photon excitation up to the Rydberg states for 2 qubit gates. And we're using blue and infrared light for that 2 qubit excitation to NS states. Our gate set consists of the following capabilities. We can perform global rotations on the qubits with microwaves. And so these are arbitrary rotations about an angle in the XY plane of the Bloch sphere by controlling the phase of the microwave. We perform single site gates using a combination of microwaves and optical Stark shifts, as I'll describe, and then the Rydberg interaction for controlled phase gates, CZ gates, which, depending on the state we go to, can be at site separations up to about 3 sites or more. And then combining that with local rotations, we have a controlled NOT gate. The neutral atoms are very interesting since they have capability of native implementation of multi-qubit gates, and indeed the Toffoli gate, 2 control atoms, was demonstrated in the Lucan group a couple of years ago. So here's some older data showing microwave rotations. This data was at 10 kilohertz. We've since increased the amplifier driving the horn, and we're now at about 75 kilohertz Rabi frequency. Using randomized benchmarking, we can verify 2 to 3 nines of fidelity on these operations. And then to do single site gates, we do that in a couple ways. If we just want a phase gate on a single site, we focus a single off-resonant laser beam to give a local Stark shift, and that implements a Z gate. And we actually use one of the Rydberg lasers to do this. If we want a local X or Y rotation, we combine a local Z gate with the focused laser beam with 2 microwave pulses. So if I perform a microwave pulse of -π/2 and then +π/2, that leaves the qubit state unchanged. And if I insert a phase operation in between those 2 pulses, I get a rotation of the qubit. So that's how we do local X or Y or any angle around in the equatorial plane. So here's some examples of this kind of data. This is with qubits spaced by 3 microns. And here we're performing a local X rotation on the center site. And we're doing that with this -π/2, +π/2 microwave operation that leaves all the red sites here unaffected. And then on the central site where we insert a local Stark shift, we could get Rabi oscillations. And we can do that on multiple sites just by using deflection of the Stark beam to multiple sites. Here's an example of data where we're driving local oscillations on two sites at the same time. Similarly, for the Rydberg operations, where we're using tightly focused beams, here we're focusing the blue and infrared excitation beams on the central site, and we drive ground Rydberg Rabi oscillations on that site, and very little happens on the neighboring sites. And so, for example, after a pi pulse, we can turn that site from bright to dark without affecting the neighboring sites. Okay, so that's a single qubit control. And then for 2 qubit gates, we're using the Rydberg interaction. And as I already mentioned, in the ground state, these hyperfine clock qubits are very weak interaction, excellent quantum memory. We drive up to these Rydberg states. Depending how high we get a very strong interaction. If we went up to 100S, we'd get 3 gigahertz at 3 microns. And so we have this great increase in the interaction state. And then we use Rydberg blockade to prepare entanglement. And depending on how high up in the Rydberg level one goes, one can produce a stronger and stronger interaction, which underlies the path towards very high connectivity. We haven't reached this level of connectivity yet, but certainly we believe it to be possible as we continue to progress the system. So the experimental geometry looks like this. We have our trap array in a vacuum cell. We have a pair of facing high numerical aperture lenses. We project the trapping light into the cell. We have 2-dimensional acoustic scanners for the 459 light, for the 1040 light, and also for the rearranger light, which is 1064. And then we collect the light with a camera for measurements. So the sort of standard gate in this field, which goes back to the original proposal from the year 2000, is this Rydberg blockade gate with a sequence of 3 pulses, pi, 2 pi, pi, where one excites the control atom, one of the states of the control atom to the Rydberg level, 2 pi rotation on the target, and then returns the control qubit back to the ground state. If the control was sitting here, nothing happens. If the control started in the 1 state, this excitation gets blocked, so we get a conditional phase shift, and that leads, in the ideal limit, to a perfect CZ gate. This is the original protocol. There's a lot of other protocols possible, and I'll mention some of those in a moment here. But I'll just show you our implementation of this protocol from a couple of years ago first. So here's some data that we use as part of the tuning process of this gate, and this is described in this paper, where we have 2 atoms that we're working with, and we excite one of them or not to the Rydberg state and look at the effect of that excitation on this neighboring site, and we insert this sequence of pulses, or insert into effectively a Ramsey sequence of microwaves, so that we get 2 curves that are pi out of phase. Stated another way, if I perform a microwave pi by 2, a Rydberg 2 pi, and then another microwave pi over 2 pulse at a varying angle, I'll get this Ramsey fringe, the red data here. And if I first excite this neighboring atom to Rydberg state, that will block the 2 pi rotation and block the phase, so I get a fringe that's pi out of phase. And so we use this pi out of phase condition to tune in the parameters of these pulses. But this is really the conditional dynamics that you see in this eye diagram, and then combining that with the effectively Hadamard gates or X rotations before the Rydberg pulses, and then microwave pulses to verify the entanglement by looking at parity oscillations. We can derive a Bell state fidelity, which in this experiment was about 0.89. And this fidelity was really limited not by fundamental issues, but by various technical imperfections, laser noise, optics, atom temperature. And so let's take a closer look at that gate and understand what we really should expect. So, as I said, in the ideal case, this gate should give a perfect controlled Z, a perfect entangling operation. In reality, there's 2 sources of error. One, the Rydberg states where we're putting population have a finite lifetime, so there's radiative decay from those states, which gives some decoherence. And furthermore, this blockade interaction that blocks the target excitation, if the control is being excited, that blockade is not infinitely large. So there will be some residual excitation, which breaks the protocol. And one can analyze how those errors scale. So the blockade error scales as the ratio of the blockade strength divided by the Rabi frequency squared. And the spontaneous emission error scales with the amount of time one spends in the Rydberg state. And that's inversely proportional to the rate of excitation, the Rabi rate. And so we'd like to make the Rabi rate large to minimize the spontaneous emission error. But if we do that, then the blockade will not be effective, because the ratio of blockade to the Rabi rate will not be large. It would make the Rabi rate large. And so minimizing the sum of those errors, you can find an optimized fidelity given by this expression. And it scales inversely with the product of the blockade strength and the Rydberg lifetime to the 2/3 power. Okay, so that's how the fidelity scales. And then you can look at the atomic physics. The blockade strength naively scales as the principal quantum number to the 12th power. That's the scaling of the Rydberg-van der Waals interaction. And the lifetime scales as about n cubed. And so you might expect the error to scale as 1 over n to the 10th. And so if I go to high enough n, I should be able to make the error arbitrarily small. In fact, that's not correct. because we've neglected the fact that there's not just one set of Rydberg states here, but there's many states. And so a more detailed analysis that includes also neighboring Rydberg levels, and that you can find that, for example, in this paper, shows that one has to consider off-resonant excitation to neighboring Rydberg levels. And so the blockade strength can never be larger than the actually the qubit frequency in the ground state, and the separation between neighboring Rydberg levels, which scales as the Rydberg constant divided by n cubed. And including that off-resonant excitation, asymptotically at high n, the product of b tau is constant. It does not continue to improve, but in fact asymptotes to a constant. And so what the optimal Rydberg level is to get the highest possible entanglement and gate fidelity really depends on specifics of the particular atom's atomic structure. And so we looked at that in some detail for rubidium and cesium and used master equation simulations of quantum process tomography. And for these atoms, depending on exactly how one wants to do it, there are different choices for the optimum level, but they all lie sort of in this range here. And the simulations show that you really, at room temperature, cannot get beyond something a little bit less than 3 nines. If you go into a 4 Kelvin cryostat, you can increase tau, the Rydberg lifetime gets longer, and so you can make this somewhat better, but it's not really adequate in terms of scaling the system. So one needs to find better protocols. One way of making a better protocol is to do pulse shaping such that we can make the Rabi frequency fast, yet suppress leakage to neighboring Rydberg states. And that's something we did with Frank Wilhelm's group in this paper, where we called it a Rydberg drag gate derivative removal by adiabatic gate. And the idea there is essentially the same pi 2 pi pi protocol, but instead of using constant amplitude square pulses, we use shape pulses, where the envelope of the pulse is being specifically shaped to minimize coupling to these neighboring Rydberg states. And again, the calculation gets somewhat technical, and I'm not going to go into the details, but doing that pulse design, and this really was motivated by an approach that was initially introduced in the context of superconducting qubits and was part of the big progress in superconducting qubit gate fidelity a decade ago. But applying that to the atomic case, we were able to predict that we should be able to reach gate fidelities of better than 4 nines at very fast times. So 50 nanosecond gate times, 4 nines of fidelity. And if we allowed ourselves to think about a 4K environment, we could even push that up to 5 nines. So in principle, with some careful design of the pulses, one could reach very high fidelity in this system. Now, nevertheless, this type of pulse sequence is somewhat inconvenient, and that we need to apply very rapidly a pulse to the control atom, a pulse to the target atom, and a pulse back to the control atom. And so this requires a very fast optical switching system. And we wanted to do this in a simpler way, and that led to some studies of symmetric protocols where we apply the same pulse sequence to both atoms simultaneously, which simplifies the requirements on the optical control system. And there's, again, many ways of designing this type of symmetric controlled phase gate. And I'll just show you here one that I think is really very nice because it's extremely simple. And we developed this in this last paper here, but also independently. It was done a little bit before by the group in Wuhan in this paper. And this consists of a single shaped pulse, which we took to be a Gaussian envelope. And the Wuhan group used a slightly different envelope, but it's the same principle, and a constant detuning. So you could hardly think of something simpler. You just apply a single smooth pulse to both atoms, with a time-varying Rabi frequency at a constant detuning. And the result of that, if applied adiabatically, is that both the one atom and two atom Rydberg coupled states start in the ground state, get partially excited, and return back to the ground state. And the phase accumulation during that pulse, if it's designed correctly, corresponds to a perfect entangling phase gate. The condition for maximal entanglement is that twice the phase picked up in the one atom case, where you have one atom in the ground state that's Rydberg coupled, minus the two atom phase is equal to pi. And so that's the simplest possible gate. We have not actually demonstrated that in the lab yet, but we've been using a somewhat different gate and also doing that with an improved control system. So based on that 0.89 fidelity result from a couple of years ago, it was clear we had to make some technical improvements. We've been heavily engaged in that in a collaboration between the university and Gold Quanta. And Gold Quanta has built their own computer and will be making it available over the cloud in a couple months from now. And this involves an improved quantum processing unit with more stable optomechanics, custom vacuum cells with electrodes for controlling the field environment, higher numerical aperture lenses, and actually dual-sided imaging to get more photons out, improve control electronics. And so we've been using this to improve the gate fidelity and start to run circuits. Part of the improvements are also lower noise lasers, and that we've improved our laser locks for long-term stability and lower noise. This is a self-heterodyne spectrum of the servo bumps on our locked lasers, which are now well below minus 50 dB relative to the carrier. This is actually quite significant for getting the best possible gate results, and one can also quantify the influence of these residual servo bumps on the pulse errors. Let me not go into detail about that. So here's the result using this new system, using a symmetric protocol, but a non-adiabatic protocol. This is the protocol introduced by the Harvard group a couple of years ago. And we did this with a single, somewhat larger beam addressing two sites. So this was two sites, 3 microns apart with a beam waist of about 7 microns and using the n equals 75 state. So this was a gate in the very strong blockade regime. The calculated Rydberg interaction is about 1 gigahertz. And the sequence to prepare a Bell state is a global microwave pulse, a pi/2 pulse, the Rydberg interaction, and then a global 3 pi/4. That sequence gives you a Bell state. Here you see ground Rydberg oscillations with good coherence, and here you see the 2-atom ground Rydberg oscillation that has the root 2 speed up. And with this implementation, we achieved a Bell state fidelity of about 0.95, correcting for state preparation and measurement errors. So that was a good improvement in a dense array, but it's not really suitable for running circuits because we don't have the individual addressing that we really want for circuit operation. So we've then extended that to using small beams. So these are now beam wastes close to 3 microns. This is at a larger spacing, about 9 microns. And this is no longer a blockade gate. So here we've modified the pulse parameters such that even though the interaction strength, the blockade strength, is only less than twice larger than the Rydberg excitation Rabi rate, we can still get a very high fidelity entanglement. And here we reached a Bell fidelity of about 0.96. So this is individual addressing, high fidelity, and this is now what we need to run circuits in this system. So let's see, before going on to circuits, I'll just mention the current status for gate fidelities with Rydberg interactions. So there's the result from Harvard using large beams. They reach 0.97. There's also an unpublished result from Wuhan with larger beams. They've reached 0.98. There's the strontium result with large beams that's reached 0.994. And then there's our result, which is now up to 0.96, but using small beams. And really, one needs to do these operations with small beams or come up with some other ideas in order to make this compatible with scaling and running circuits. And how long is it going to take before we can push this 0.96 up to 0.99 and beyond? It's hard to predict. This is the result of experiments in my group over the last decade, where we started just over the threshold for entanglement, and in a sequence of experiments have continued to push the fidelity higher and higher. So we're now at this 0.96 level. When exactly are we going to get up into the really high fidelity limit? Well, time will tell, but it's clear that the areas where we need to improve to really achieve this is to continue to make things more stable, make the atoms colder, have very good beam quality, low laser noise, stabilize the electric field environment, and automate the tuning system to really take this out of the hands of students and postdocs, but really automate the process of tuning for the best possible performance. And these are all engineering issues, not physics issues. So I feel very confident that we can continue to progress this system and reach very high fidelities. So with that, there's been a lot of work climbing this path to doing quantum computation. And let me then show you where we are in terms of running circuits. And the near-term goal is to reach some kind of quantum advantage. We don't yet have computationally useful quantum processors. Really, classical computers are only useful because they have error correction. And in some sense, it's somewhat remarkable that reliable computation with imperfect devices is even possible. And this was pointed out a long time ago by von Neumann in this very interesting paper. But although this is taken for granted in the classical world, as we know, quantum error correction is very difficult. The overheads and resource requirements for quantum error correction are demanding, to say the least. And because of that, there's a lot of near-term interest in exploring what we can achieve before we get to error correction. And hybrid algorithms that combine quantum circuits with classical optimization loops are a possible path to quantum advantage. And we've been testing quantum circuits for VQE, QAOA, and also phase estimation recently in my group. And let me share some new results on running QAOA algorithm on this hardware. So the quantum approximate optimization algorithm, or QAOA, is one of the most actively investigated hybrid algorithms at this time. And you can think of this as a discretized or trotterized version of adiabatic evolution, in that one applies a sequence of operations that involve a mixer Hamiltonian with some classical strength, beta, and a problem Hamiltonian with some classical strength, gamma, and one applies a sequence of mixer and problem to drive a initial superposition state into a state that solves the problem of interest defined by this Hamiltonian. And one uses a classical optimizer loop to find the optimal classical weights to drive that quantum state evolution as rapidly as possible to the ground state of the problem Hamiltonian to solve the problem of interest. And so the problem that Farhi and Goldstone used when introducing this, and one that's of interest, is the max cut graph problem. And this involves considering a graph with connected nodes and finding the groups to allocate those nodes to that maximizes the number of connecting lines that connect nodes in two different groups. And so this is basically an Ising problem. And so the problem Hamiltonian for this is given by a product of sigma z operations on connected nodes -1. If the two nodes are in the same class, then ZZ gives me a +1. So that term is 0. So that would be, say, these two nodes. If the nodes are in opposite classes, ZZ is -1. So this gives me -1, and that drives the Hamiltonian to lowest energy, which solves the problem. This is classically a hard problem, and that there's no polynomial time algorithm that can find the optimal solution for arbitrary graphs. And although it's kind of an abstract graph problem, there are plenty of practical applications of this calculation. So here's the sample circuit on a simple triangle graph, and expressed in the neutral, so that's the logical circuit. And if we express that in our neutral atom gate set, including swap operations, if these were not all directly connected, it's already quite a long circuit. So we've been looking at this on small systems. Here's the first example for a 3-node QAOA graph, where qubits 1 and 2 are connected, qubits 2 and 3 are connected, and so the max cut solution is for the central qubit to have the opposite state of the other two. And here's the p equals 1 result with giving an approximation ratio. It's essentially the overlap of the result with the ideal result, 66%. And we do a second cycle, so a deeper circuit, p equals 2, we can push that up to 71%. That's 3 qubits. We've also run this on a more ambitious 4-qubit circuit. So here's 4 qubits. The 3 outer ones are connected to the central qubit. And so again, the max cut solution is the central qubit is in the opposite state of the other 3. And then we've run this for p equals 1, p equals 2, and p equals 3, which is quite a long circuit. For p equals 1 and 2, the results continue to improve, and we reach, for p equals 2, an approximation ratio of 0.65. For p equals 3, the result starts to decay again because the gate errors are accumulating. I will need to move on in about 5 minutes, so I'm going to wrap up here and just leave a few minutes for discussion. Here's this noisy simulation of what the results were. This would be the ideal case. This is for a 3-qubit circuit. This is a very noisy case. We're able to look at what we achieved and the simulations and get a good handle on what our gate errors and dephasing rates are. So this is work that's being prepared for publication. There's other modified forms of QAOA that may work much better. And let me just summarize by saying, I think neutral atom qubit arrays are a very promising platform. We've reached good gate fidelities in the system, and we have now the first results running quantum algorithms. So I'll stop there, and I take about 5 minutes for discussion. Thank you very much.
У меня микрофон не работает. Hello. Mark, thank you very much for the nice lecture, and we have some minutes for the questions. Any questions from the audience?
Thank you for your lecture. I have 2 questions. The first is, what's the maximum level of connectivity currently achieved in neutral atoms? And the second is, as far as I know, Rydberg atoms are quite sensitive to external electric fields. So is it necessary to control them? Thank you.
Sure. So, I mean, in terms of running digital circuits, this type of connectivity here is really the largest that has been demonstrated to date. Again, by going to higher Rydberg levels and adjusting the gate protocol such that only a relatively weak Rydberg interaction is required, one can in principle push this connectivity out much further. So this circuit is being run not in the strong blockade regime, but actually in a regime where the Rydberg interaction is only a little bit stronger than the Rydberg excitation rate. And so this is a 9-micron separation here. And so I think we can certainly push this out even further. As one goes higher in Rydberg level to achieve longer range coupling, more connectivity, the sensitivity to electric fields does increase. And we deal with this in two ways. We're using special cells that are really a specialty of cold quanta that have electrodes inside that allow us to use spectroscopy of the Rydberg state to null out the electric fields. Even so, we see some variation over time from the electric fields. And what we do is we apply short wavelength blue light just from an LED to the cell. And this keeps the electric field environment more stable. So one does have to take some care with the field environment.
Okay, Mark, and we have 3 questions from people staying in the lab in Moscow State University. Okay,
Sure.
The first one is...
Okay, so first question is, what are experimental challenges for double magic trapping implementation?
I think it's quite clear based on this analysis how to do it. We just have not done it yet because we're busy with other things. But it's one needs to put some sideband frequencies on the trap light in our calculated approach, and I think this should be relatively straightforward. If the trap light is very high power, there can be some technical challenges in terms of phase modulating this high power light, but I think this is certainly doable.
Okay, the second one.
Okay, what are the reasons for readout errors, especially from lower qubit state?
Yeah, so I mean, the fundamental issue with the readout is that one has Raman transitions. If the polarization of the light is not sigma plus, we'll get some Raman rate from the other excited states. And I mean, it's the same situation in trapped ions, but trapped ions have very strong traps where, because they're using Paul traps, using RF fields to confine the ions, the trapping potential is greater than KT at room temperature. And so even though one heats the atoms during readout, one doesn't lose them. In the neutral atoms, if we use sigma plus readout, we don't have 3D cooling. And so in order to use sigma plus to eliminate the Raman, but do the measurement fast enough with small enough amount of scattering not to heat the atoms out of the trap, you need to collect a lot of photons. So the challenge is there's several issues that are coupled together, but one needs to have very good optical access and high collection efficiency to minimize Raman rate or heating rate while doing the measurement.
Well, and the last one.
Okay, how strongly the blockade gate fidelity depends on the choice of a particular pair of array sites?
Sure, so the best result we saw was 0.96. I mean, we saw a couple % variation. So here we have tuned up 3 different pairs to perform this circuit, 3 different controlled C gate pairs. And we saw a couple % variation. And the atoms are identical, but there can be small differences in the tuning of the alignment of the beams to the different sites. And when we change the pointing of the beams, the intensity changes a little bit. So these are all just questions of doing a better job on the tuning to make this more uniform.
Well, okay. So any other questions or comments? Okay. One more question.
Sure.
So thank you for a really in-depth lecture. So my question is about the cross term in the energy shift formula. I can't quite understand where this term comes from exactly. Can you elaborate on that?
Sure. So again, it's somewhat technical. The details are in the paper I mentioned from a few years ago, but you can think of it as the magnetic field is mixing states. And so we're admixing different Zeeman states into the Zeeman states that are being used for the qubit encoding, and that admixture changes the sensitivity to the light shift. So those different states, given a particular polarization of the optical field, gives you different coupling to the light. So there's a connection between the strength of the magnetic field and the strength of the optical field. So it's a next order in the interaction Hamiltonian between the atom and the magnetic field and the light field.
Okay, Mark. So thank you so much once again, and see you somewhere.
See you somewhere. Thank you.
Yeah,
All
bye-bye.
the best. Yeah, yeah. All right.